Also, what I want to start chit-chatting about today, though, is modeling. Modeling. Why would I care about talking about modeling? Sorry, I got the Crocs I'm going to trick myself with. Modeling.
So you're also into fashion.
I am fairly into fashion. I think it screams that when I walk in the door with my bright green Crocs on. Modeling gives us a very specific, sometimes they use two L's. Modeling, they have a very specific idea that comes to mind when you talk about modeling. Who do you think of? Say it again, I'm sorry, nice and loud.
Heidi Klum.
Christy Brinkley, Heidi Klum, Christy Brinkley, Billy Joel. I think of Billy Joel, I think Christy Brinkley should be married. You think of people. You think of people, that's physical modeling. Physical modeling, getting up, putting clothes on, standing up, blah, blah, blah. We're talking about mathematical. Mathematical modeling. What does this mean? Bikinis covered in equations? I wish. I think there might be a market for it. Maybe. But not for this class, because I want to keep my job. No. Mathematical modeling. The loose definition of mathematical modeling is looking at data. And this is why I like it. You look at data. You examine the shape of that data. And when I say shape, we'll talk about what I mean by that as we go through today and for the next 2 or 3 weeks together. And you try to find an equation that quote-unquote fits the data. Quote-unquote fits the data. So basically, it has 3 parts. Number 1, you collect some data. And I don't think we'll have time to actually collect any data today. I have some data I want to share with you guys and play with. But I think we'll have to save the collection of data for after the exam on Wednesday, which is okay, I don't mind that. You're going to collect some data, then you're going to examine the data, and then you're going to try to find an equation that best describes the data.
That best describes it.
Yes, ma'am. I'm going to put best in quotes. That best describes the data. Collect some data, examine the data, and then try to fit a model. So the model, if you will, is an equation. And mathematical modeling means you're trying to fit the equation, a mathematical equation, to some kind of a data set. I have to do this all the time. All the time. I can't wait. I just collected some yesterday with my son. I ran a cyclocross bike. I bought it used about, I don't know, 6-7 months ago. And it had cantilever brakes on it. Cantilever brakes. Any bikers in here? Cyclists in here? Okay, cantilever brakes went out of style with like Wham in the 80s. I mean, they're extraordinarily low torque. You pull on them, it takes a long time to stop. I've wrecked a couple times already with it. Not because I'm careless, but because I'm used to disc brakes. And I'm used to things called V-brakes. V-brakes are, contrary to popular belief, they're shaped like a U. So they have this U shape, and they pull, and when you grab those things, they stop very, very quickly. So I retrofitted the V-brakes onto my cyclocross bike, which took all afternoon yesterday. And then I did a mathematical test before and after to see if it actually did make me slow down more quickly. The raw numbers look like they do, but I have to fit a model to it to be able to prove it to myself mathematically that I didn't just waste an afternoon $50 doing that. I feel safer. I almost ended it this morning coming into work. When I came down that hill, the hill by the dorms, I come above the dorms, down that trail, around that like cell tower they built up there, whatever the hell that thing is up there they put up behind the dorms. And then I came down that really steep hill behind the dorm, down the really super steep hill over here that somebody told me there was parking next to now. I guess there's parking over there now. And then I come rocking in right to the top of Grandview, and then I brake. With the cantilever brakes, I have to start braking back at the flat part. So I started doing that. As soon as I came down that hill at top speed, I hit the brakes and my rear tire lifted up. Because the front brake had grabbed so well, I'm like, well, let's let that back down and then feather them as I come in, because obviously they seem to have a lot more braking power. But I check the braking distances and we'll see if it equates that way too. So anyway, this is useful stuff. My son was all about it. He's 6 years old. He's like, Daddy, let me help. Where did you stop? You skidded. You can't count that data point. It's 6. I've already ruined it. So the interesting thing about this data is it can take on any kind of shape. And there are entire branches of mathematics devoted to all kinds of mathematical modeling. But we're only going to break it down to 3 different kinds that pop up in the world. I have markers over there. There's 3 different shapes that I want to look at in this class. 3 different shapes of data. Okay? So we've got data that looks like one of these 3. So what I've got here is just an x and a y axis. And I'll label it in a second. So sometimes data looks something like this. Ish. Now, you guys are used to algebra classes, where you get a data point, another data point, another data point, another data point, and they're beautifully perfect, right? They're gorgeous, absolutely perfect as they float up. Then there's reality. There's things called sampling error that prevents perfect data from occurring. As a matter of fact, if you see perfect data, the movie The Fugitive. The movie The Fugitive, some of you have seen it with Harrison Ford. It's based off, I think, an older movie or an older book, I believe. The crux of the movie is he becomes a fugitive. An old TV show. Thank you, Asani. Thank you. The crux of the movie is that, I don't want to give too much away, but he has to go on the run because he finds out something about forged data. And if you remember the movie, at some point they go, the data look too good. Too good. In other words, not enough like this and too much like that. And here's the deal. In reality, data never looks perfect. It always looks close to a pattern with what's called sampling error around it. We're going to start analyzing that, if not today, first thing on Wednesday after your exam. This, essentially, you can see the behavior. As we go from left to right, we can go from down to up. It's somewhat predictable. What shape, if you had to draw a shape to kind of go through that data, what kind of shape would you draw? Most probably a line. It's the simplest. Could you draw kind of a squiggle like this? You could, but why would you? Ha-ha! You logged on, you SOB. You could. Sorry, ADD. You could. Say that again?
It took an hour.
It took an hour, I know, exactly, almost exactly an hour, I know. That's why I call it IT. You could put, for example, a squiggle through it, and maybe you might want to. I'll show you some very, very interesting data using looking at CO2 emissions from the Mauna Loa Observatory on the Big Island of Hawaii that actually looks a lot like this, but upon closer inspection actually has a squiggle going on. But in general, you don't have that. This is what's called linear data. And we're going to look at that from a linear modeling point of view. Some data, as x gets bigger, y gets bigger. Now, it doesn't have to just be x getting bigger and y getting bigger. You can also have x getting bigger and y getting smaller, something like this. You can also have that situation. But the kicker is, both of those shapes, whether you're looking at the orange one or the green one, seem to have pretty arguably a straight line going through. Pretty arguably a straight line going through. So if a line is the best mathematical construct to describe a data point, or a set of data points, we call that linear mathematical modeling, or just linear modeling. That's what we're going to start today. That's what we're going to start today. The other two, you know what? Let's just hold on to the two until we get to them. How's that sound? Or do you want to see an overview? What do you think?
Let's do an overview.
Overview? Go with an overview? Okay, overview then. The other two, not everything is linear. The next data set we're going to collect, after we collect a couple that we're going to do today and Wednesday, you're going to go outside with me on my bike, and I'm going to start. I haven't figured out which hill we're going to do this on yet. It's got to be big enough to generate some fun speed. I'm thinking the Grandview going the wrong way might be kind of fun. Yeah, breaking the law.
You break, you handle it.
But if you look at my speed, and I did this yesterday testing my new brakes, I started at the top of my neighbor's very steep driveway and let go. Just let gravity pull me down that hill. Well, if you do that and you're graphing the amount of time it takes me on my bike versus how long I go on my bike, it does not do this. It does not do this. Because if it did that, that would mean for every additional second I'm on my bike, I go like 5 more feet. So after 1 second, I've gone 5 feet. After 2 seconds, I've gone 10. After 5 seconds, I've gone 15. That isn't what happens when you lose your brakes on a bike or a car. What happens? You go faster with time. What's cool is you go faster predictably. So what might happen is it might start looking like this, but then it's going to rocket upward. So it might start looking linear, but then curve upward, if you will. That, if we do it that way, if you were to reverse engineer the curves the other way, and this is where it does get interesting, it would do something similar going the other way. I do that in a dotted line because that won't actually, I do that with a dotted line because I want you to see the shape that actually a free rolling body takes on Earth when subjected only to the force of gravity, which you'll see soon enough with me on my bike, assuming I don't bite it doing it. What shape do you see right there? It's your parabola. That might be kind of hard to see if I didn't show you the other side of it. Now, I'm not saying this part exists with me in my bike, because it won't, okay? I start from 0 and start going faster. But I wanted you to see the other shape to let you know the shape that's actually going on is a parabola. So this would be called quadratic modeling. Be quadratic modeling. And you might remember them a little bit from your study of Math 65, maybe Math 95, a little bit. You might also remember that parabolas don't always open upward.
They go down.
Sometimes they open downward. Why would we care about that on Earth, you think? Uh-huh. Sometimes parabolas can look like that. And Asani brings up a very, very good case. If you're shooting something, anybody shoot distance, like distance at targets, maybe 1,000 meters, 1,500 meters, thank you. And what do you have to allow for?
Depend, wind, gravity.
Good, gravity's the big one. Wind is actually, isn't talked about with this model at all because it's a third variable, if you will. But gravity, there's an old question, if you're on a perfectly flat section of Earth, say 2,000 meters of perfectly flat Earth, which sounds ridiculous, but there actually do exist places like this. Like there's a test track over in, I think it's Germany, it's exactly 5 miles long. And you fire a gun and drop a bullet at the exact same moment. Which one's going to hit the ground first? We have one vote for they hit the ground at the exact same time. We have a second. Bruce seconds that. Who says the one you drop hits the ground first? Okay, we got many votes for that. Who says the one you fire hits the ground first? Nobody says that. The correct answer is they both hit the ground at the exact same time. Because the force of gravity pulling downward has nothing to do with horizontal motion, only vertical. So as soon as you fire that thing, it's cool. It's very hard to see the visual. But when that thing starts going, it immediately starts dropping at the same rate the one you dropped drops. Because the horizontal velocity has absolutely nothing to do with the vertical. The only way it could be different is if there was some kind of a rifling issue that created lift. But I don't believe it does. I think all rifling does is keep it going straight. Am I speaking correctly?
Yeah.
Not Michael. Not Michael. David. Damn it, I was going to say David next! Because for some reason I connected it to Ryan's middle name. There we go. David, right?
Whatever works for you.
No, it's not David. David, what's your name?
It is David.
Isn't that your middle name or something?
Mm-hmm.
Yeah.
But it's Ryan's. Well, Ryan's your middle name?
Yeah.
Okay, but you go by Ryan. I got the connection now.
Right on.
So anyway, that's quadratic modeling. And we care about quadratic modeling when we're talking about projectiles on Earth, or we're talking about speeds on Earth under the force of gravity. So basically, gravity is quadratic. So this happens a lot. This happens a lot. Watching Max try to shoot foam arrows through windows. I have to concern myself with gravity and also air resistance. We won't talk about air resistance. And the third that I want to talk about, and there are many others, but these are the only ones I really want to talk about in this class. It looks similar to quadratic modeling, or at least it can look similar to quadratic modeling. It's the kind of growth that starts kind of slow, and then eventually ramps up. And it looks similar. It really does. I mean, it's very hard to distinguish between a quadratic model. Say that again.
Does it go down?
And that would be a cubic model, which is a great, great choice. It's not going to go back down like a cubic or a quintic would do. It's not what it's going to do. Say that again, Andrew. No, we're going to avoid square roots for the most part. This thing is going to flatten. If you were to reverse engineer it back this way, it's going to flatten out.
Oh, okay.
And eventually, it never goes flat, but it flattens-ish. Does anybody remember, or has anybody ever learned this kind of behavior? It is exponential, Benji, thank you. That's an exponential model, and we care about that because that's how your money grows. That's how bacteria grow. That's how housing prices sometimes grow. And sometimes fail.
But it never hits zero.
Correct. The idea of exponential growth, theoretically, is that it never goes to zero. Now, theoretically, it never goes to zero. Realistically, it might as well. So, for example, we're going to talk in here about presence of drug or impurity in a system and how a filter knocks that down. So, you know, things have half-lives. Aspirin, for example, has a half-life. Or Tylenol. You take an Advil. Take 2 Advil, what's that, 500 milligrams? Let's make up a number. 500 milligrams. I think Advil's got a half-life of something like 8 hours, which means after 8 hours, whatever you ingested, your liver has filtered out, or whatever filters. Is it liver that filters drugs and alcohol? So it filters out half. So if you take 500, 8 hours later, you're down to 250. 8 hours after that, you're down to 125. 8 hours after that, you're down to like 67 or something like that. 8 hours after that, you're down to half of that. 8 hours down to that, you're down to 32, then 16, then 8, then 4, then 2, then 1, then a half, then a quarter, then an eighth, then a 16th. So you see, you're kind of going this way on the curve, or if you want to draw it better, you would draw it this way. We'll do both of those as we go through this course together. You know, like this. Okay. Exponential decay would go this way. This would be exponential growth. But the idea is that number, those fractions I was telling you, they never get to 0. 1/32nd, 1/64th, 1/128th. They keep getting smaller. I mean, you know, 1/8 is about 12%, 1/16th is about 6, 1/32nd is about 3, 1/64th is 1.5, but they're never going to get down to 0. But the question is, are they arguably 0 to a point? And the answer is yes, because eventually you have to take more Advil because there's so little left in your system that you have to put more in. But the problem with that, as you may have heard, is that certain drugs become residual in your system. And they never really go away. They just sit there resident in your system forever. Certain drugs are worse than others. So the question is it a problem that we've got 0.0000001% Advil in our spine left over from, 30 years ago and had a headache? And the answer is probably not that big of a deal. Probably not that big of a deal. So yes, it never goes to 0, but you can treat it as though it does when you take more. Does that kind of make sense? Fair enough, good. That's the 3 kinds of modeling I want to get into today. Well, no, I lied. I want to start by talking about this one. We'll get into these as we kind of develop a need for those. And what I like about this is this takes us right into probability beautifully. This exponential model takes us right into probability perfectly, where we kind of tail off the course. So I'm thinking we spend about a week in each of these bad boys. Then we start prop stat for the rest of the course. And we get into that. Fair enough? Cool. I'm going to stop that for a sec. And let's see if